Hi everyone, in this video I'm going to show you how to compute the Joule-Thomson coefficient from the van der Waals parameters A and B at a particular temperature. And to begin, we'll use the definition of the Joule-Thomson coefficient for a van der Waals gas that you find in the book and also in your protocol and also in your pre-lab question. And that is that the constant pressure heat capacity, molar, times the Joule-Thomson coefficient is equal to 2A over RT minus B. All right, and that's approximately equal, by the way. It's not exactly equal. So then we'll say that our Joule-Thomson coefficient is going to be this equation with CPM divided by both sides. And we get 2A over RT minus B all over CPM, like so. Okay, let's start out first with 2A over RT, and let's just begin writing down our quantities. 2 times 1.355, and this is decimeters to the 6th, bar, mole to the -2, right up there. And then down below, we've got to choose an R. And since we have units of bar up there on the top of the numerator, it makes sense that we would choose the R that's going to allow us to cancel that out. So down here, I'm going to put 0.08314 decimeters cubed, bar, mole to the -1, Kelvin to the -1. And then our temperature, last of all, 300 Kelvin. Okay, let's check out our units first. Kelvins cancel out. It looks like one of the moles, inverse moles, will cancel out, so we get mole to the -1. The bars cancel out. And then for decimeters, that whole term cancels out, and this 6 becomes a 3. And what are we left with? 0.1087 decimeters cubed per mole, like so. All right, let's do the next step. 2A over RT minus B divided by CPM. We're going to take the expression we found up above there, 0.1087 decimeters cubed, mole to the -1. And then subtract our B value. Looking up there, it's 0.0371 decimeters cubed, mole to the -1. Then we've got to divide by our CPM, 20.785 joules, mole to the -1, Kelvin to the -1. All right, right away our moles cancel out, but I also notice another problem. I'm going to need the Joule-Thomson coefficient to be in units of pressure that we can work with. And I can begin to see the units of pascals, which, remember, 1 pascal is equal to 1 joule per meter cubed. But up here, I'm seeing decimeters cubed, so I need to convert those to meters cubed, so I'll be able to eventually convert to pascals. So I'm going to do multiplied times 1,000 cubic decimeters for every 1 cubic meter. That's going to cancel out those two like that. And then right down here, I should get 3.445, there's my sig fig right there, times 10 to the -6th Kelvin meters cubed joules to the -1. But this right here, this unit right there, is inverse pascals because of this relationship right up there. So I can immediately say that this equals 3.44 times 10 to the -6th Kelvin per Pascal. And now the final step requires us to convert to megapascals so we can compare directly with the value that we find in our books. So our mu JT is 3.44 times 10 to the negative 6th Kelvin per Pascal. But then we have to multiply times the conversion between pascals and megapascals. 10 to the 6th pascals for every 1 megapascal. These two just cancel each other out, and we're left with 3.44 Kelvin per megapascal. And we can compare that directly with a value that we can get from the book or online or elsewhere.